Hi, my name is Matheus and I'm going to present my project for the course Wireless Communications. The name of my project was Evaluation of a Coexistence Scheme for Heterogeneous Wireless Technologies in TV White Spaces. So first, what are white spaces? White spaces are those frequencies allocated to a broadcasting service but not used locally. They are mainly abandoned television frequencies from VHF and UHF that were abandoned due to the switchover to digital television. In 2007, bigger companies like Microsoft, Google, Dell, HP formed a coalition to try to regulate the use of these white spaces. On November 4th, 2008, the Federal Communication Commission finally approved the use of unlicensed spectrum under certain requirements. Here there's the result of a spectrum analyzer, and it's possible to see there are several bands of frequencies that are unused, several channels that could be used for communication. They are unused, especially here where the old analog TV channels operated. So in 2014, IEEE released a new standard called 802.11af that is also referred as Wi-Fi and Super-Fi that uses these white spaces. It allows WLANs operations in TV white spaces in the VHF and UHF bands between 54 and 7090 MHz. First, before using, the provider must query a geolocation database to discover what frequency channels are available to use at that given time and position. One advantage is as you use lower frequencies for transmission, there is a longer range that can provide long-range internet access to distant and remote areas. And it accepts up to 568.9 megabits using MIMO technologies. There is an image about the availability of TV channels for using across the US. It's possible to see there's a lot of green areas that corresponds to plenty of TV channels available. So the problem of the project that has to be solved is, for example, how different technologies must coexist in these TV white space bands. How do they share all the available unlicensed spectra? There is a need for an efficient coexistence management scheme to coordinate access from different networks and types of networks. And the spectrum utilization, it must be maximized while guaranteeing that harmful interference is kept to minimum. So for that, the paper by Khalil and other authors was used as a reference, and their idea was implemented. So now I present their idea, and then I show the implementation. So the idea of their paper is a two-stage coexistence management scheme, which is centralized, has a database management. The main purpose is to increase the spectrum reuse. It's separated in two stages. The first stage is called bandwidth allocation. It allocates the bandwidth to the network such that the fairness is achieved while maximizing the reuse of spectrum. And it has two steps: the network subset division and the interlinear programming maximization. The second stage is the channel assignment. After having a certain bandwidth for each network, then the total bandwidth is divided into channels and they are assigned to different networks. And this stage is subdivided in channel assignment and then channel assignment augmentation. For the simulation, two tools were used. First, MATLAB, and for MATLAB, an extra library was used called optimization interface toolbox. It's a free MATLAB toolbox that it's used for solving optimization problems, linear, nonlinear, continuous, and discrete optimization problems. And C++ was used for the channel assignment stage. So the first step, it's called finding. It's about finding the network subsets. So the first of all the space, the networks are represented in a graph. For example, here, each vertex is a network, and an edge represents interference between networks. So 2 cannot use the same frequency slots as 1 or 5. However, 6 and 7, 6 can use the same slot as 5. 7 can use the same slot as 5, but 6 and 7 cannot share the same frequency slot. So the main idea is to find out how much bandwidth can each of the networks take. But for the first step, the first algorithm is about separating for each network 2 subsets. Disjoint subsets, for example, 3. For 3, one subset would be 6 and 7, and the other subset would be 5, because they can reuse the same bandwidth, the same frequency channels. Here's the algorithm implemented. First, it starts, it's an iterated algorithm that starts empty, and then by checking the edges, and it finds the network subsets. The second step of stage 1 is the integer linear programming bandwidth maximization. The idea is to maximize the minimum bandwidth among networks given a set of rules and constraints. So here, the main idea is to provide fairness so that one network doesn't have all the bandwidth and the other one have lower bandwidth. So by maximizing the minimum bandwidth, we solve. In other words, solving this problem, we can solve this fairness problem. And as output, there's a certain bandwidth is allocated for each node. Then for stage 2, the first step is the channel assignment. Channel assignment, after having certain bandwidth allocated for certain networks, then there's a need to now go to see in the spectrum all the slots available, and then assign these slots to certain networks. So they are assigned not in a random manner. First, the networks are sorted in descending order of their degree in the graph, and then they are assigned one by one to each network according to the algorithm. And last stage is this channel assignment augmentation. The idea is because it's if there are leftover channel slots that for any reason was not assigned, then these leftover slots are assigned to the networks with least amount of bandwidth allocated in stage 1. So now I'll show the code running. This is the main algorithm. It runs the stage 1, reading from a file. The G is 1G is the interference graph that is declared as a matrix, as one can see here, and then it's defined the maximum bandwidth for each network, number of slots, the slot size, and several constraints And also for each network, here I use 1.5. It's the minimum size for the slots. It depends on if it's LTE or WLAN. Here, to make it simple, I just assign the same slot size, the minimum slot size. So after running step 1, here for each network there are two disjoint subsets. For example, the neighborhoods of net 1 are 2, 4, 5. The algorithm found that, and also found that the subset 1 is 2 and the subset 2 is 4, network 4. Here for network neighbors of network 3, one subset is network 5, another subset is network 3. And if we see here, that's exactly right. Having this network, one subset would be 6 and 7, another subset would be 5. And when it can't find any disjoint subsets, then the subsets are empty. After this part, the next part is allocating the bandwidth. As it's shown here, it gave 3 slots to the first, and the all other ones got 2 slots. After running these optimization problems with a lot of constraints and inequalities and integer variables. So after assigning the slots with algorithm 2, then the channel augmentation part. The idea is by recursively reconstructing the graph the networks that had least bandwidth, they are augmented with the leftover slots. So here, before augmentation, just one slot here. After augmentation, there were 2 slots. So after results, it's possible to see here got the same results from the paper, the network ID and the available bandwidth. 3 shares the same bandwidth with 1, 5 shares the same bandwidth with 6, and here they share the same bandwidth. So we achieved bandwidth reuse, spectrum reuse. So as a conclusion, it was presented in this project an implementation efficient coexistence scheme for TV white spaces. Better performance could possibly be achieved if a distributed approach was used instead of centralized one. And white spaces, the use of unlicensed arrays has a lot of potential to spur new technologies by the increase of coverage area and to expand access to affordable broadband. Thank you.